So walkthrough for our example, this is the RVE we previously shown. We have the fiber matrix interface elements shown as such. And here we have all the different input that you need for this model. Now notice there's 20, 30 different inputs you need. And a lot of times on the data sheets, you only have the modulus in the fiber direction, the modulus in the matrix and also a fiber failure criteria. And everything else is either got in very advanced testing, or you have to extract. So we'll show you and walk you through a process in which we can automatically extract these different values. So let's take an example, a longitudinal calibration. We have a coupon that has fibers aligned in the direction of the load. And when we load it up, you see the multi-scale simulation on the left, that the fiber is starting to bear most of the weight. And we start to have the fibers break close to the failure stress. A lot of times on the material data sheet, you'll have an average modulus and an average strength. Or if you're lucky enough, you'll have a stress strain curve. Next, the transverse calibration, we have fibers running in the orthogonal direction to the load. So here's another multi-scale simulation where you'll see as the coupon extends, you start seeing debonding and matrix nonlinearities. And here you also have a modulus strength or even a curve. Also, we have some shear calibrations that helps you look into the in-plane shear that's seen within coupon. So in this multi-scale simulation, you have plus minus 45-degree shear test, and you start seeing the damage and strain occur in between, in the matrix in between the fibers. And a lot of times you have a curve here, and you can make an RVE to fit this curve. So here, I'll open up the previous RVE that we're working on, and I'll show you how we can use the new optimization tool to extract these different parameters. Navigate to materials, and let's say we'll start with something simple, the fiber direction and the fiber failure. Usually this is not coupled, and it's really dominated by the fiber stress. A lot of times you'll have the tensile stress, but you may not have is the strength statistics and the Weibull distribution. Let's say we know the shape parameter, or you can come up with a shape parameter that you want to tailor to your material, but the scaling parameter is something that's a little tougher to find. So if we don't have it, we simply leave it blank. And what MultiMech will do when you select run, it'll look for possible variables. And once it finds this variable, it will bring up a dialog box that shows you the different variables you did not fill out. It gives you a few options. One, it's like you forgot to fill it in. It'll give you a chance to fill it in, and then you can run it. Next is a design of experiments. What you can do here is you put in a minimum value and a maximum value of this, and you can run a gamut of different values in between. And this is for something like a sensitivity study. They can see the results of this material, and you can gauge how this variable affects the results of your microstructure. Or finally, you can run optimization, where you put in a minimum and a maximum value of where you think this value will be. And what you do is you have a target you want to hit. In this case, we have, say, a max value that we would like to hit, a max stress in the 1-1 direction. Type in the fields, and we can put in a certain value. In this case, we want 2,000 megapascals, and we can add it, and we now have a target. You can see here that we can add multiple targets, so you're not limited to just one max value. You can also fit to a curve, first value, last value, etc. Once we have this, we can put in the optimization inputs. You have a global and a local optimization algorithms, and these are evolutionary algorithms that we use to hone in the global scale and then refine the solution in the local optimization. Select OK, and it'll run however many iterations that you choose for both of these, and it'll also quit out once you have a certain criteria for hitting a minimum value, and it'll output that in the dialog box here, and it'll show you the different results and the amount of error you have. So from this specific optimization, I can show you the results we received. So here are all the simulations that computer ran. What it does on the right, it takes all the simulations and it orders them from the amount of least error to most error. So you see case 4, which is one of the first cases, has one of the worst errors. And you see that one of the last simulations, 21, had the closest solution. And a good way to visualize this is looking from the bottom and seeing how the algorithm slowly honed in on the perfect solution. And in this case, we actually got within 0.01% of a target. Okay, so I showed you how to use a optimization tool for a single variable, but a lot of times these parameters are highly coupled. For example, the matrix has dominant properties in the transverse direction, but also has a lot of properties that defines a lot of properties in the global composite and the in-plane shear. That's also true for the interface properties. So between these two, we have, well, first let me fill out the solution that we just found here. We can go back to the matrix properties, and we see that we don't know anything about the damage law here, so we can take away these two variables. And so we're already at two variables, but we also don't know anything about the interface. So we can take out this parameter and this parameter. So now we're sitting at 4 variables. Doing this manually is borderline impossible because you'd have to set up a huge parametric study, run hundreds of tests, and just feel it out yourself. Well, with the new optimization tool, you can now input all 4 of these variables. So it's identified the 4 variables that are left blank. And just like you did before, you put a min value and a maximum value for the M and the lambda, and for these two. Now you can get creative and notice that maybe the tensile and shear interface strength, they might be linked, or they might be very close in their strengths. So what we can do is actually take this and we can link this variable there. So now instead of 4, we have 3. This is a way to cut down the number of variables that you have. In this case, we are going to fit to a curve. The curve that we have listed is a curve, say, in the transverse direction. So what you do is you input a Excel sheet, and you have these different strains and stresses. And what MultiMech will do, it'll actually take those strains and it'll apply it to the RVE to hit your target and try to link with these variables. In this case, this is in the 2-2 direction, applied load 2-2 direction, and after you upload the CSV file, you add it. It's also worth mentioning that you're not limited to only testing one direction at a time. What you can do is, this is in the transverse direction, but let's say we didn't want to do the last solution and we wanted to put them all together. Well, that's possible. You can do another target, say you can fit the max value that we did previously in one direction. You add this, and so now we're testing in both directions, so we can have basically all the tests done in one big optimization. And the same way we can run however many global iterations, usually 20 or so is a good number, and however many local optimization algorithm steps to take you to the best solution possible. Now, this seems like a lot, and you'd wonder how long it took to find an optimal solution. Well, in this case, we got to a solution that matched the curve within 0.5%, and the time it took to run all of this was 30 minutes. So very doable. So even if you want to do more variables or bigger models, you can definitely run these, and they'll run potentially overnight, and you can really extend the intricacy of this optimization. And in this case, I'll show you the results we got from that. And here's the stress and strains in 2-2. And you see, just like we saw before, we have the best result 31 first. And you see how the solution improves as we go to the top. And what we can do is show the best solution and compare it to the target. And you see here how closely it follows with it. And at the very end, you start seeing a little difference in the failure. Okay. So that was the optimization showcase. And when we say reverse calibration, we want to be clear that we're not, whenever you hear reverse engineering or calibration, you think you're calibrating a model to something you already know, or to a set of data that you already know. So what's the point of it? Well, in this case, we're actually calibrating the RVE. And what RVE does, when we add, we're simply adding information. We're adding the DNA of the RVE to it. And we're helping build a characteristic, fully inclusive single RV that can represent any load case. So for example, in this case, we have a complex layup that 0, plus 30, 0, negative 30. It's a very weird layup and not traditionally used. We actually take the microscale and we can observe the different loads seen here. We can see here that we have a high axial load in the fiber, but we also have a lot of strain and a lot of damage occurring around there. And because we calibrate for both of them, this single element can actually represent both of them simultaneously.